The topic of discussion today is related to failure rate data. Where does failure rate data come from? I mean, everyone is, very happy that they can pull a number off of a drop-down list. Some people question the value of that number. Where did it come from? A little bit. And there's kind of an illusion that there is a absolutely sacrosanct source of the absolute truth that's in one of these documents. These guys, OREDA, tend to get a lot of credit for being the ultimate source of truth. But what you're going to see when I go through this process is that picking a failure rate is more of a research activity where you're finding clues about reliability data in multiple different places and trying to resolve all of the conflicting data that you're getting from multiple different sources to come up with a number that's actually going to be relevant to what you're doing. So I'm going to begin in the SIL verification clause. So if you look at the IEC 61511 standard, there's one clause that really defines what SIL verification is. And although you could write a 300, 400, 500 page book or technical report on how to do SIL verification, the amount of information about it in the standard is actually pretty small. It's all contained in clause 11.9, which is the quantification of random failure. Boy, that's a topic for another seminar. When we're running these calculations, the standards committee, the people who know and understand SIL verification really understand you're only looking at random hardware failures. If you start trying to put errors related to human failure in here, not only does it not help you, it actually makes your design worse. But that's a topic that I'm going to have to push back for another day. Here we're looking at failure rate data. So the standard says I need to determine by calculation, so you need to do a SIL verification, that I have achieved the calculated failure measure for each SIF. So I need to calculate what its failure measure is. Maybe that's a risk reduction factor. Maybe it's a SIL. Maybe it's a dangerous failure rate, depending on what mode of operation you're using. So you need to calculate what you expect that SIF to achieve, compare it against the target measure, and make sure that what you calculated is better than the target measure. Then in 11.9.2, you drill down into the details of, what do we need to consider? Well, I need to consider the architecture, and then items B, C, and D all talk about failure rates. So I need a failure rate of dangerous failures that are detected by the diagnostics. We call them the DDs. Then I want failures that are undetected by the diagnostics but detected by proof tests, which are the DUs. Then I need failures that are undetected by the diagnostics and undetected by proof tests. Those are the DNs, are the never detected. We look at susceptibility. So there's a whole lot of other things here, but the key is you need to consider what the failure rate is when you're running your calculations. And anyone who knows how to run these calculations, this is very obvious to you that we're going to get failure rates. We're going to split safe and dangerous. We're going to look at diagnostics coverages to determine what is detectable and what is not detectable. So clause 11.9.2 lays out the things that you need to think about when you're running your SIL verification calculations. What I want to talk about today is the rest of the clause 11.9 that doesn't get a whole lot of attention. And I'm going to go, actually, I'm talking about 11.9.3, 11.9.5, or 4. 11.9.5 actually should be an informative note as opposed to a requirement. Basically, it's guidance that tells you if you don't meet your SIL target, these are the things that you should think about to try to change your design to achieve the SIL target. Important information, but informative, definitely not normative. Okay. So let's look at clause 1193, which is really going to be the driver of the discussion today. So 1193 says the reliability data used when justifying the effect of random failures shall be credible, traceable, documented, justified, and shall be based on field feedback from similar devices used in a similar operating environment. Wow, that would kind of question how you could ever even justify using FMEDA data from equipment vendors. Well, I'm going to save that discussion for another person, but the FMEDA data that you get from equipment vendors, you could make an argument that there's a lot of field feedback that is baked into those numbers or baked into the failures of the components. And they do consider operating environments to some degree at a high statistical level. But what I'm going to show you toward the end of the discussion today is you really need to be very concerned about where your data is coming from, and you have to think about who accumulated the data, what is the environment in which they collected that data, and are there failures in that data that don't show up in your application? Or are there failures that show up in your application that aren't in that data? And we'll go through that process just simply by looking at a solenoid valve and digging down into those details. Okay, so credible. So how can I believe that the data is reasonable, that it was collected in good faith, that it was collected thoroughly and accurately? Traceable is kind of easy. So when you're running your SIL verification calculations and you're presenting that final information in a report, you need to be able to explain where that data point came from. And if you're using Vertigo, the world's best SIL verification software, that's pretty easy because most of the time that's going to get tracked back to our database, and our database is going to get tracked back to an analysis that I will show you a little bit later. Okay, there are some notes. This includes user collected data, vendor provided user data, data from general feedback, etc. Note 2, the lack of reliability data reflective of the operating environment is a recurrent shortcoming in probabilistic calculations. End users can organize relevant device reliability data collection. So kind of, yeah, we don't have really good data from the field. I wish we had better data from the field. Please go collect that data from the field is what note 2 is getting at. And note 3, vendor data based on returns can be restricted to a population where there is full knowledge of the operational environment. Vendor data based on returns, I've gone over this in webinars in the past, is pretty much a horrible way to collect data, to represent data, because, well, a vendor doesn't know what happens to their devices after they leave the factory floor. They don't even know if they're actually even ever put in use. And if they fail, there's no way to know that the person is going to return the device, especially if it's low cost and a hassle for them to return it. So vendor data based on returns, it can be useful, but the vendor has to be exceedingly careful about tracking the devices they create out into the field, which most of the time, especially for smaller, inexpensive devices, is generally not the case. Okay, clause 1194 talks about uncertainty, and basically I'm going to shortcut this discussion and say the official mechanism for reliability data uncertainty is that 70% confidence limit that's baked into a lot of the assessments, and it's going to be contained in data that you get from equipment vendors. It's going to be contained in data that you get from Kenexis, for instance, in our database. All right, so that's what the standard says, and we're primarily concerned about clause 11.9.3 here. How do you know that the data that you're using is good enough? Okay, so let's what I'm going to do now is I'm going to go into KISS. I'm going to make things a little bit bigger so that they're legible by human eyes. If you've seen one of my webinars, you're going to see me go into General Oil and Gas Operating Company, which is a fictitious company that we use for webinars and demos and training classes. And I'm going to go into their SIS design inside our Vertigo tool. And I'm going to pop open their safety instrumented function list, and then I'm going to drill down into one of the safety instrumented functions. So I've got Interlock 101A here, and you can see that Interlock 101A has sensors, logic solvers, and final elements. If I drill down into the sensor, you're going to see all kinds of information about how it's tested, what is the basis for selection, what is its status. This one is actually active. I should have converted it there. Voting arrangements and so on. But then you have something up here called the type. So a type is a category of instrument that you may have many of these. So right here, you'll see I've got pressure transmitter generic is the type of device, and that's going to be for PT 101DA, 101DB, 101DC are all of this type of transmitter. You'll see I've also got a failure rate here for the connection of the device to the process, which gets added in. But so as you see here, this type of sensor is going to have these lambdas associated: safe detected, safe undetected, dangerous detected, dangerous undetected, and dangerous never detected. And that dangerous never detected is going to be based on this manual proof test coverage that you see down here. So this data came from somewhere. Let's drill into the details. So I'm going to close this here and show you that these numbers actually came from our database. So if I go here into sensor types, this is going to show me all of the different types of sensors that are in this study and where they came from. So I'm using a pressure transmitter generic. Where did my pressure transmitter generic go? Here we go. So pressure transmitter generic high trip has this overall failure rate, percent safe, safe coverage, dangerous coverage, and then that's used to calculate the lambda values. You'll see some interesting things to note about our software. This is grayed out, which means this item is not connected to the library. So I typed this in manually as opposed to getting information out of the library. If it's green, for instance, for this pressure transmitter Yokogawa EJX, that means that this device is consistent with what's contained in the Kenexis library. If something was inconsistent with what's in the Kenexis library, it would be red. So the data that's stored in a project is going to be separate from the data that's stored in the library, very deliberately, because if we make a change to the library, we don't want that to change the results that are contained in any particular study. So on a regular basis, you go in here and you make sure that what's in your study is consistent with what's in the library. If I wanted to bring something in out of the library, I can simply add new sensor type, and then it's going to go through that gigantic list of everything that's in my library. So let's go ahead and take a look at the library. So if I go out to the main page in KISS, I can click here, and that's going to bring me to the library manager. On the left, you're going to see all of the company libraries that you have access to and any custom libraries that you might have created. And I also, or everyone who uses our software will have access to Kenexis Standard. So if I go to Kenexis Standard and I look at sensors, this is going to be the full library of all of the devices. And of the devices, you're going to see basically two types of devices. You're going to see failure rates that are associated with a particular vendor. So I've got a combustion analyzer, Amatec WDG. V is a specific make and model. And this is going to tell me what is the failure rate, percent safe, architectural constraint type, and then we're going to have this cool thing over here called the database reference. And that's going to give us traceability, another one of those key terms, traceability back to where that data actually came from in the Kenexis data registry, which I will show you under the hoods, the inner workings of what happens at Kenexis, so you can understand where these numbers are coming from. This one is actually pretty easy because if we have a make and model and a vendor name, that data came from the vendor without a doubt, no question about it. That vendor gave us the information, and that vendor might have created that information themselves. They might have gone to a certification body like EXITA. EXITA is a great certification body. TUV Nord, TUV Rhineland, TUV Süddeutschland, or TUV Product Services are all good. I could go into a whole discussion about what certification bodies you can trust and which certification bodies maybe you should think twice about. But when you see a number here in the Kenexis database, you know that the people at Kenexis vetted the certification and agree that the certification was done properly, and thus we are willing to publish it. And I assure you, Kenexis has gone into a lot of situations where the vendor said, here's our certification data. We looked at the third-party report, we looked at their data, we said this is garbage, we're not publishing this. We don't believe what you're telling us. You know, when you tell me a single ball valve is capable of achieving SIL 3 with a single device, right out of the gate, I can tell you you're full of crap, and we're not publishing your data. So there's the stuff that comes directly from the equipment vendors, but then there's another type of data that we call the generics. So I'm going to go to pressure transmitter generic. So if you know what make and model of vendor you're going to, you can use that vendor's data directly. But as always, there's the caution to say that vendor's data is for your piece of equipment only. It doesn't include the connection of that piece of equipment to the process. So the failure rate for the process connection would need to be added in separately. And it also makes a lot of assumptions about the environment that you're putting in the equipment into, some of it which might not be true. So a lot of operating companies don't use FMEA data from equipment vendors and instead use more conservative generic data. That the other benefit of that is that it's applicable across the board. So when we at Kenexis say pressure transmitter generic, we're kind of looking at the full range of available devices and picking a conservatively high failure rate that would be representative of the entire category instead of kind of cherry picking something real good. Okay, so you'll see that we picked generic pressure transmitter, generic high trip. This is the failure rate. This is the percent safe, safe coverage, dangerous coverage, architectural constraint type. And then we have this database reference 1.111 and database revision. And this goes back to the Kenexis internal ISO 9001 controlled process that we have for determining what data is appropriate, what data is relevant. So This is in the database. You, the end user, could just pick this and carry it over into your study and start running calculations. But now we're going to kind of open up the curtains and let you look at the great Wizard Oz and see what's going on in the background. So I'm going to temporarily close out of here, and I am going to go into the inner sanctum of Kenexis information. So under our controlled software, ISO 9001 controlled, we have the failure rate data, which was updated just yesterday. So this is something that we spend a lot of time maintaining and updating. If any of you know Mr. John Applegate, he's in charge of our data collection and monitoring efforts. And this is darn near a full-time job, keeping track of all the data that's in our database. So if you remember back to here, there is a database reference 1.111. Well, if you look at our spreadsheet, you'll see that there is sensors, pressure, generic, and then 1.111. Actually, let me make this full screen and make this a little bit bigger so that it's actually visible. Okay, so you see that we have a generic pressure transmitter. When I click on this, it's going to take me to that specific data sheet, and you'll see the details of how we came to the conclusion that we came to. So you'll see information about what the equipment item is, what its type is, what its function is, manufacturer model, constraint types, database revisions, blah, 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 all of the information for when the device was last updated. And then what you're going to see are the pieces. So we don't have just one piece of information. We got data from ISA's Technical Report 8402. We got data from Syntef. We got data from Smith. We got data from CCPS. We got data from NPRD 95, NPRD 2016, Safety Equipment Reliability Handbook. And you'll notice that the data from here we didn't use. And you see that? OREDA. And in this case, I'll show you in just a second, the data is not that good. So we actually have to go and critically analyze each one of these data sources to determine how was the data collected, how much data was collected, what is the environment that the data is collected in, is the data point even valuable enough for me to put onto this spreadsheet for further consideration. So before I go into how we came up with our final decision, let me start by going through some of these data sources. And actually, let me go backwards a little bit. So I'm going to go back to the table of contents, and I'm going to actually go to generic pressure switch, because generic pressure switch has an extra category here called KF, and it's got some other data sources that you didn't see. So when Kenexis is coming up with a generic failure rate, we're going to go through a whole pile of information. Now, let me see here. I need to temporarily stop sharing so I could see what you guys are seeing. But right here, I can't even show you the whole thing. There is, this pile is a small subset of all the data sources that we're looking at. So let's kind of jump into what those sources are and what they look like and whether or not we're getting value out of them. So yes, we're going to look at the Exida Safety Equipment Reliability Handbook. So here is the SERH, kind of putting that up in front of the camera. excellent source of data, but when we use anything from Exeter, whether it's the Safety Equipment Reliability Handbook, you're also going to see right here the EMCRH, which is the Electrical and Mechanical Equipment Reliability Handbooks, which are more kind of pieces, parts, as opposed to complete finished instruments themselves. The thing to remember when you look at these data sources is that they themselves contain a lot of subjective analysis, and that's something that we consider when we're doing this process. So when the SERH says that the failure rate is 6 and that the safe failure fraction is 40%, that's not directly based on a analysis. I'm sorry, I shouldn't say analysis. It's not based on a field data set. So it's not like there was a collection of switches out in the field and the devices were tested, the failures were tracked, and that information was published directly. What you're getting out of these handbooks is very similar to what you're seeing on the screen here, where data from a number of sources was collected and reviewed to determine what's reasonable. Okay, the next item up is good old Smithy. So Smith, let's find the Smith book. The Smith book, the latest one is right here. Reliability, Maintainability, and Risk from David Smith. So in the Smith book, there's going to be a section at the end, if I can find said section. Appendix 5 is failure mode percentages, and Appendix 4 is actually going to be general failure rates. Now, the failure rates in this book are closely associated with David Smith's database that he uses. Let me see if I can find it. So Technis is his company, and Faradip 3 is the full database. So I don't have a copy of Faradip 3, but it's something that I want to get access to, obviously, because it's important to what we're doing. So if you look in the Smith book, he's going to give you low, mean, and high. So low is 1E minus 6, mean is 5E minus 6, and high is 4E minus 5. So what you see right out of the gate is that if you look at the actual measurements that come from different places, there is a wide, could be much larger than an order of magnitude distribution between low failure rates and high failure rates. And that distinction is based on how the devices are designed and how they're used, and we'll get into that in a little bit. Okay, so those are the failure rate numbers, but what we didn't get is failure rate distributions. And that goes to one of the difficulties here, where you really need to take data points from a bunch of different places. You might get a good failure rate from one resource and a good safe fail split, or safe dangerous split, from another resource. So it's detective work, it's analysis of a lot of different resources. All right, NPRD 95, so that would be this guy right here, non-electronic parts reliability data. This information is collected by the Reliability Analysis Center in Rome, New York. So this is NPRD 95. This is the first volume of NPRD 2016. So tons of data in here. But now when you're looking at the NPRD data, what you have to understand is, where did the data come from? The Reliability Analysis Center is I don't want to call them a government agency, but they make almost all of their money subcontracting to the federal government in the United States, specifically the military. So when you look at data points from NPRD, and I'm going to bring up a data point real quick, you have to remember that that device, the data that you're looking at, might have been collected in a Jeep in combat. It might have been collected from a boiler in an aircraft carrier, which is a completely different application than what you're looking at in a chemical plant. So if I open up NPRD here, let me make this bigger, let me rotate it and kind of scroll it open. So here are some examples, and I kind of highlighted this. So you can look at, contactor failure rates. So I've got a contactor, it's an external contactor, ACU power, and APU line. The application is military. And then you're going to get not one data point, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different data points from different studies or different tests. So one of these might be related to data that was collected off of a electrical substation at a military base. One of these might have been in an aircraft carrier. So a lot of different data points were collected, and actually in this case the failure rates are all fairly similar to each other, which is kind of surprising. I'm used to seeing more of a spread. So if you go down here to magnetic contactor, you've got a 1.6, but you've also got a 219.3 here. So the NPRD data, there's a lot more data for a lot of different applications, but it's not coming from chemical process plants for the most part. So that's something to consider and use your expert judgment on when you're actually doing your analyses. Okay, next item up here was a heavy water reactor assessment that came from the Nuclear Regulatory Commission. We've got data there for a 5% confidence limit and a 95% confidence limit. And then some notes here about how we determined what the safe failure fraction was based on that data set that we looked at. And yeah, the new reg stuff is usually pretty tight because the nuclear power facilities have historically had a nearly bottomless pile of money to spend doing maintenance. So when you have a lot of money, you can spend more money collecting data, doing maintenance, and so on. So a couple of nuclear sources. IEEE. So the IEEE Gold Book, we got a data point from that. And take a look at these numbers though. So for these nuclear applications, you've got 3 to 9 to the minus 6. This nuclear application, 2e - 7. So in these more finicky is not the word I'm looking for, but installations where they have more money to spend and they're able to take better care of their equipment, the failure rates are going to be lower. Whoa, shocker. So it's not that failure rate. What this should be telling you is that failure rate is not just a function of the device. How it's used, how it's designed are critical in determining what that failure rate needs to be, and you need to think about that when you're running your applications. So this IEEE number is fairly low. That's going to come from the Gold Book. So Mr. Kevin Mitchell, my partner here at Kenexis, we found the Gold Book, we found the Red Book. These went out of print still like when I was in high school. These things were out of print. We were able to get these data points. And you would think that older data would be worse. That, we would have a higher failure rate. I mean, more modern equipment should be better, shouldn't it? No, not necessarily. Older equipment was generally built with a lot more safety margin. When in doubt, build it stout. The washing machine that my mother used back in the 70s and 80s, it had very few moving parts that were built stout. That thing never failed. The washing machine I bought for myself about 5 years ago has failed twice already because it's got a lot more complexity, a lot more components. Don't get me started. So the age of the data is not necessarily representative of the frequency of failure. You need to understand how it's designed and it's applied. Okay, so we had a data point for NPRD 2016. And we also have a couple of these confids. So the confid KF, I have a different document that I could go find out what KF is. But basically, Kenexis is exposed to data being collected from our customers. You'll probably know that our Kenexis Vertigo SIS design basis tool allows you to collect data. And a lot of times our customers ask us to review the data. And then with their permission, we take a genericized, anonymized version of their data and include it into our data sets. So we have air pressure switches and gas pressure switches from data collected from a customer. And if you look at these applications, instrument air, generally benign in comparison to, maybe 500-degree vacuum gas oil. Natural gas purchased from a utility is generally benign in comparison to something like a refinery fuel gas. So we know that these failure rates are going to be on the lower side in comparison to what we would expect in a chemical plant, pharmaceutical plant, or an oil refining type application. Okay, so these are the data points that we collected that we thought were credible, that we thought were reasonable for this application. Now, let me show you some of the data points that we didn't give you. And one of the guys that you'll note that we didn't use is here, OREDA. A lot of people look at OREDA and say this is the archetype. This is the best source of data because, look at this book. It's so thick. It's got so much data in it. And we published this one. We got this one in 2002, back when Kenexis was just me and Kevin. And actually, at that point in time, we weren't even Kenexis. But I digress. And we've got another one here from 2015. Well, before you go and use your gut to say, I've heard OREDA so many times, it's got to be good, let's go take a little deeper dive into what this data looks like. So let me begin by showing you some good data. So if I maximize this and I show you data, this is for a control and safety equipment, ball valves in gas service. Okay, so in OREDA 2002, which was this guy here, we have a whole bunch of failures and things to look at. Keys, up here in the top left. The population means this data set is based on 224 valves. Now you're probably thinking to yourself, only 224? OREDA, I thought they collected all the data from everybody in the North Sea. No. There's only 224 valves in this set. And those 224 valves come from 17 installations, so 17 platforms, and obviously more than one valve per platform. And for all of the failure modes, so of those 224 valves that were in operation for 6.5 calendar years on average, different data sets are going to be for different durations, there were 87 critical failures. So failure to close on demand, 52, failure to open on demand, 26, spurious operations, 6, and so on. So this is pretty good, and if you go and look at Kenexis's generic numbers for a ball valve, we will show you the OREDA data because it's pretty good. But what about a different type of instrument? So let's go and let's look at a OREDA data for a capacitance level. Okay, this again is in our 2022 data. I've got one instrument on one platform, one instrument for a total of 0.03 years, 0.04 years, I'll be charitable and round up. What value is this? One instrument for a fraction of a year. We looked at this and said, yeah, I'm not including, this is worthless to me. There's not enough information for just an insignificant period of time. Why am I even looking at this? Well, maybe if we go all the way out to 2015, we'll have accumulated more data. Well, that's kind of not the way it works. So the data in the 2015 version doesn't include this. So each one of these, whether it's 2002, 2009, 2015, they are their own entity and they're not necessarily combining all the data together. Now, if you want to do that and create an OREDA superset for yourself, you're at liberty to do that, but that's something that you're going to need to do. And unless, like Kenexis, you can afford to have somebody almost full-time just looking at data, probably going to be cost prohibitive for you to do. All right, so this is 2002. Let me show you another data point that we did not use. We rotate this guy and make him bigger. Here we go. All right, so CPU of an emergency shutdown system. This came out of that 2015 data set. So 2015, we've got to have a lot of data to work from, right? No. I have one CPU in one installation for approximately 2% of 1 year, and I had one spurious trip. This is useless. This is worthless. Don't even bother even including this in your analysis. So when I hear things like, oh, we want to use OREDA because it's the ultimate source of the truth, there's some good data points, there's some bad data points, but you can't just go to one book. You're going to need to look at the full range of everything that's available, put it all on a spreadsheet, look at it, and do something with it. So what do we do with it? All right, let me bring back up that spreadsheet. So here you'll see that we did some analysis. We determined what is the arithmetic mean. So arithmetic mean, you add all the failure rates together and divide it by the number. We also did the geometric mean, where you multiply all the failure rates together and then take the nth root. When data is distributed logarithmically or exponentially, a geometric mean is going to be closer to the truth than an arithmetic mean. And then we're also going to look at the median. So if I've got 9 data points, sort them from highest to lowest, what is number 5? That's going to be the median. And do we actually run with one of these? No. We look at these numbers and then we look at, okay, so I've got a geometric mean of 1e minus 6. I've got an arithmetic mean of 5e minus 6. I've got a median of 1.2e minus 6. Looking at these two numbers, you would think that maybe we would want to go with something like a 2e minus 6. But expert judgment says, okay, these numbers, this number is probably optimistic. This number is probably optimistic. This number is in a very non-severe service. It's probably optimistic. So maybe I should be a little bit more conservative and lean toward the numbers that are more like a process industry application. And then based on that, the analyst uses their judgment. That judgment then gets reviewed by the Council of Elders here at Kenexis, and we pick a number to go with. So analyzing the full scope of data and using expert judgment is absolutely critical. Now let's look back. So that's where the numbers came from. If you've ever wondered where a generic number came from, you're going to see these numbers in the database. You're going to see this database reference and that equipment ID reference all contained in the Kenexis Vertigo database. Now you know where it came from. So let me give you one last thought before I kind of break it up for the day. What you're looking at is a solenoid valve. And I'm bringing up the solenoid valve to talk about how the failure rate can change based on how the device is used and how the device is designed. So when you look at this typical three-way solenoid valve, on the left-hand side, you're de-energized. So when you're de-energized, this plunger, so if you can see where my cursor is, the plunger is down and it's seated against the instrument air supply, preventing the instrument air supply from going forward, but the vent is unseated, so you're able to go from the process valve here, you're able to go out and vent to atmosphere. When it's energized on the right-hand side, the plunger is pulled up by the magnetism that's created here in the core, and now you have a pathway to go from your instrument air supply out to the valve. But you'll see we are stretching the spring here, whereas when you de-energize it, the spring goes back to its compact position and pulls that plunger down so that it seats on the instrument air supply side. So now, when you're looking at a failure rate for a device, FMEVA, look at what all of the components are and look at how those components can fail. So what are the components? We have a manual operator that you could screw and unscrew that'll fix it in one position or the other. That shouldn't cause a dangerous or undetected failure because you shouldn't be monkeying around with that, and a lot of times you'll just remove it. The fixed core is what creates the magnetism. So that's the core of the solenoid. Then you're going to get the solenoid itself as these things with the X, and really they're shown kind of as two lobes in the cutaway, but this is kind of a circle that encapsulates that core. When the solenoid is energized, you magnetize the core. When it's de-energized, you demagnetize the core. Here in green is the plunger. It's the thing in the valve that actually moves. It's the thing in the valve that actually seats. So you've got the plunger. The spool is kind of attached to the plunger, and the armature is kind of like a valve bonnet that holds everything in place. You've got your input connections, your output connections, you've got your springs. So you need to think about how this can fail, so you go through every component and kind of say, well, what are the failure modes of that component? So let's talk about a couple of failure modes. So the primary failure mode for a solenoid is coil burnout. So this coil, I mean, you see a big red X here, but you're basically talking about hundreds or thousands of loops of a copper wire. And when electricity flows through all those loops, it creates magnetism. Well, those loops of copper wire are separated by varnish. As time progresses, the varnish wears away and you start to get short circuits. As you short circuit, the number of loops decreases, which decreases the magnetism, which causes the current to get higher, which causes it to get hotter. And then as it gets hotter, the varnish wears away faster and you get a vicious cycle to where the coil no longer creates enough magnetism to overcome the force of the spring, and you fail. That fail is going to put you into this safe position where you vent out your actuator. Now, for that failure mode, is it just a number that you can get out of a Bell Core database? Well, that's what is going to happen when you get an FMEDA. They're going to have to pick a number for how often that coil fails. But is that number constant? Is it an inherent property of that piece of equipment? No, it's not. So if you're using a 24 volt DC, you're going to need to push a lot more current through there to get the magnetism to hold that in place. That means that this solenoid is going to run hotter than if you were using 120 AC. So the difference between 120 AC and 24 volt DC is going to be a dramatic difference in the frequency at which you're going to get a failure. But in this case, a safe failure. Furthermore, who provided the coil? Maybe one company is using 100 rounds where a different company is using 1,000 rounds. The company that uses 1,000 rounds, that coil is going to have a much lower failure rate because it's designed more stoutly. Another item that can cause a failure here is this spring. So the probability of failure of this spring is going to be a function of the design. How thick is the wire that I made my spring out of? What is its metallurgy? That's going to change the probability of failure of the spring. It's not just an inherent property that belongs to solenoid as a group. Now, another mechanism could be that this plunger right here, when we're in the open position, the plunger gets stuck in place because I can build up crap. You like that scientific term? I can build up crap on the edges here that's going to prevent it from going closed. Well, how much crap I build up, and you could build it up here to prevent it from moving, kind of freezing in place, is going to be a function of the quality of your instrument air. The lower quality instrument air you have, the higher the probability that this failure is going to occur. And there's a joke in the past I heard, hey, somebody put some air in my instrument water. Because if your instrument air conditioning is not good, you might fill up your instrument air system with water instead of air. And I'm aware of one accident in history where all of their final elements failed at the same time, common cause. How did this happen? They literally put air in their instrument water. So their air dryers failed. Their instrument air became waterlogged to where it was just water. Someone realized it was just water. They drained the system out, repaired the air dryer, but this equipment was wet for so long that as soon as you drain the water out and put air in, everything corroded and rusted over, and every solenoid valve in the entire plant failed because of all the corrosion that was generated by taking the water out of the instrument air system. So, whose data do you trust? Nobody's. You have to understand that a company that's using 24-volt DC solenoid valves that have undersized coils in the Gulf Coast of Mexico, or Gulf Coast of the Gulf of Mexico coast, is going to have a spectacularly higher failure rate than someone who's using 120 AC solenoids that are oversized in Lima, Ohio. Those failure rates are not going to be comparable. They're probably going to be an order of magnitude different. So let the buyer beware. Look at the data sources, understand their strengths, their limitations, where the data is coming from. There is no data source that is correct except for your data source. Collect your data, understand your data. Christ's sakes, all the tools are right there available in Kenexis Vertigo to collect and analyze this data. So look at your data, because it's going to consider how you design your plant, your ambient environment, how you're doing your maintenance practices. In the meantime, you can use vendor data, you can use Exoda generics, Kenexis generics, whoever generics, but always be dubious, because the data sources that the data came from, there's orders of magnitude spread in those data sets. All right, with that, I might have time maybe for one question, but I've got to be on a call with somebody else in a couple minutes here. So Chris, is there a question that that I should try to get on board with real quick?
Let's see. We have one here. It says, realizing that SIL calcs are dependent on an assumption of a constant failure rate, and unfortunately, many manufacturers now referencing section 7.4.9.5, note 3 of IEC 61508-2, which states that experience has shown that the useful lifetime often lies within a range of 8 to 12 years. How do your analysts resolve, define, and or resolve differences in defined useful life data between data sources? And then follow-up question.
Okay, yeah, no, Chris, I've got it. I'm looking at the question.
Okay.
Okay, so the useful life, you have to be very careful with that useful life and understand when the device reaches the end of its useful life, what failure mode are you going to fail to? Most of the time, going back to that solenoid example, the useful life is limited by the coil. When the coil fails, it's a safe failure. So running out past the useful life is okay, because it's going to result in a safe failure. So basically what you're telling yourself is that when I hit the end of my useful life, I'm probably going to get a spurious trip, and then I'm going to need to repair, restart my plant. Or maybe I could put in some safe redundancy to address that. So as you're looking at those end of life failures, look at your data. Look at the failure modes and effects analysis of the piece of equipment, and consider that when you're doing your assessment. Now, that last bit on the Arrhenius equation versus the Siemens database, that's only relevant to FMEDA style analyses of equipment. So if I was doing an FMEA of a pressure transmitter, I would be looking at that to determine what my failure rates are. Those things are not really relevant to actual field data that you people in the process plants are going to be collecting when you're doing your analyses. So we don't need to kind of skew the data set to try to match our environment if we have actual data from our environment. Those techniques are basically fudge factors to allow you to use data from somewhere else and try to apply it to your application. So when you're collecting field data from your plant, that information's not relevant. And when we consider data from other data sources that are FMEDA, that would be baked into the analysis. Thanks everyone for your time and attention. I really appreciate it. If you have more questions, please feel free to send me an email. Thank you.